So in this video, I just wanted to touch on some of the problems, some of the assumptions that we make with radioactive dating. So I'm going to start out with my first issue, which is working with the potassium-40 argon-40 pair. And all that I want to point out is that argon-40 is a noble gas, and gases are able to leak out of minerals or rocks, and as a result that can throw off the measurements. So for example, imagine if you had a rock analyzed and you were told that the ratio of potassium-40 to argon-40 was 1 to 3. Well, then you would interpret that as 1 over 4, so 1/4 of the parent is left, and you would take that as 2 half-lives. Imagine though if the ratio was actually 1 to 7 instead of 1 to 3. And so instead of having 2 half-lives, you had 3 half-lives. Well then, naturally, you would be multiplying by a different number of half-lives, and so your answer for the age of that rock would be incorrect. So we're always making an assumption when we're using potassium-40, argon-40, that you're actually working within a closed system, and as a result, argon-40 was not released from the rock at any point in time. The other thing I want to mention was with carbon-14. So we know that carbon-14 can only be used on samples that are organic, meaning something that was alive or is alive. The other thing that we have to remember with carbon-14 to carbon-12 is that the half-life is a very, very small number, so 5,730 years. With a half-life value that small, we've basically made a conclusion that we can only radioactively date samples that are younger than 50,000 years. And to give you an example of why we have to do that, if you were to take a dinosaur bone, and let's just say that dinosaur was 70 million years old. Well, if you take 70 million, I'm putting it in my calculator here now, and you divide it by 5730, which is the half-life of carbon-14, you would come up with 12,216 half-lives. That's a very, very large number of half-lives. It's not manageable, and you can't work with it. So that's a limitation of the carbon-14. When we work with radioactive dating, it's very important that you assume that none of the parent or the daughter has ever been removed from the rock. So I always say, when a rock gets analyzed or a bone, all we care about is the parent-to-daughter ratio. And whatever that ratio comes out to be is very important. For example, if it comes out to be 1 to 7, then we know that that's 1/8 of the parent that's left, a half, a quarter, an eighth. So we know that that is 3 half-lives. And we're going to use the number of half-lives to multiply by the half-life value to get the age of the rock. A process like leaching can actually remove parent or daughter from the rock altogether. Thereby, when you get it analyzed, you'll get the wrong ratio, the wrong number of half-lives, so you'll multiply by the wrong number. Just like parent or daughter could potentially be removed, you could also have parent or daughter that's added from an outside source. And that would also change the ratio, giving you the wrong number of half-lives to multiply by. The other thing with uranium-lead, lead is a product, so lead-206 and lead-207 is a product of uranium-238 or 235 radioactive undergoing radioactive decay. But it's also worth noting that you can also have non-radioactive lead, and so when you actually analyze and get a parent-to-daughter ratio, sometimes that non-radioactive lead gets mixed in with the radioactive lead, and you may get a ratio that is incorrect. Therefore, you would interpret the wrong number of half-lives that you would multiply by. So, there are some examples of problems that we would have. So, to summarize, we've already talked about the fact that carbon-14 can only be used on once living things. Carbon-14 can only be used on samples less than 50,000 years. We said that. We did not say this one. Uranium-238 radioactively decays to lead-207, and it has a really, really, really large half-life. And so the half-life is 4.51 billion. And so with a half-life that big, even if the rock formed as soon as the Earth formed, we would only have underwent one half-life by this point in time. So I typically say to students, only use uranium-238 for radioactive dating purposes if you're trying to date something like a meteorite that struck Earth from out in space and is way older than the actual Earth. The other thing is that we can't date a sedimentary rock. You got to remember that sedimentary rocks are made of sediment, and that sediment got weathered and eroded from various other rocks. So if you take a sedimentary rock and you date it, you may only be dating one little piece inside that sedimentary rock that belongs to one rock. And so it's basically pointless. There's no way of determining when the sedimentary rock was formed. So all you're doing is getting the date of one little piece of gravel or sand inside of that sedimentary rock. Metamorphic rocks can't be dated either. And to understand why metamorphic rocks can't be dated, you really need to understand the metamorphic process. And so anytime that a sedimentary or an igneous or a metamorphic rock gets metamorphosed, it undergoes changes. And the changes come about because of the high intense heat, the intense pressure, and the hot chemical fluids. And what essentially happens is that we say that the radiometric clock gets reset due to the high heat and pressure. So I always say to students, imagine if you had an igneous rock, and that igneous rock had underwent 4 half-lives already, and then that igneous rock finally gets metamorphosed. That metamorphic process resets the clock right back to 0, and radioactive decay would have to occur again. So if you picked up a metamorphic rock many years later, and you analyzed it, the parent-daughter ratio would certainly reveal a half-life, but it would completely forget the number of half-lives that would have occurred before the metamorphic process. So in that particular example that I just spoke about, we said 4 half-lives. So they would be completely non-existent. You wouldn't know. So you can date a metamorphic rock, but you're only going to find out how long it's been metamorphosed, and you're not going to have any information about the radioactive decay that occurred in that rock before metamorphism actually occurred. So they are some of the issues that we actually have. Again, make sure that the parent-daughter ratio is, I guess, correct or fair, and there's really no way of making sure. You can only assume that parent or daughter isotopes have never ever been added or removed. And so that's the problems and the assumptions that you make when you're using radioactive decay.